Welcome back to lecture 7. So this is about the PN junction. So far we talked about the N-type and P-type doping of the semiconductor. And now we are going to bridge two pieces of semiconductor together. Let's say one P-type and one N-type. And then we're going to have this PN junction. So this is a reference chapter from the textbook. And then this is a SAM recorded material from Master Spring and Professor Asif Khan. So this is a circuit element for integrated circuits, and you have seen this before. In the lecture 2, we talk about the metal used for the interconnect. And seems that people are still having troubles with audio connections. So cannot hear anything. Why is that? So cannot hear anything. So can anyone hear me? The only
I can hear you.
Yeah, thank you. So I also hear a beeping, and since someone connects and then disconnects. So yeah, I hear the beep too. So this WebEx, I think if someone join or someone drop, it will have the beep. This is not ideal. So let's proceed. And I think the other session actually is recorded. Also, we have some technical challenges there, but I will try to process the video and then upload to the YouTube if you wish to watch the lecture instead of joining this live session. So it's up to you. I apologize for those technical challenges here, since today both the WebEx and the BlueJeans are not working properly. Okay, so let's come back. So here we talk about the metal, which is essentially resistor. And then today we're going to talk about this PN junction. And in the circuit element, we use it as a diode. So here, if we have a P-type semiconductor and N-type semiconductor together as a junction, then we will have this PN diode. So in the circuit, symbol is like you have a triangle and then a bar. Essentially, this circuit symbol tells you that the current flow is unidirectional. So you only have the current flowing from the left to the right. And then this is the PN diode, and we are going to discuss more details why the current is moving in one direction. So it's from P side to the N side. So this is P and this is N. And later we are going to talk about the MOSFET and MOS Cap in more details. But the PN junction is a basis for the MOSFET structure. Okay, so what is the PN junction? So PN junction is like this. You have one semiconductor, let's say silicon, but you dope the silicon with different type of doping to different regions. Let's say to the left half of the silicon, you dope with P-type. And then the right-hand side, you have the N-type doping, and you have this interface between P and N, and we call this is a PN junction. So the PN junction essentially is a two-terminal device because you have two electrodes here, and the the two terminals typically will be, let's say, grounded for the N side. So we will ground the N side and only apply voltage to the P side. So this is a two-terminal device, and if we apply voltage VA to the P side and ground N side, so we will have the current flow. And we define this current as the PN junctions current. And in this slide, we're going to discuss the IV characteristics. IV means current versus voltage. So here, let's say at 0 voltage, the current is 0. This is as expected. Without external voltage, then the current is 0. This is the equilibrium state. So then the forward bias means the voltage is going to be positive. And then the forward bias, the current will be exponential increase with the voltage. To the negative side, we call it reverse bias. This beeping is kind of annoying. So let me see. So we get rid of the beeping. Or say an option to mute. Okay, let's continue. Yeah, so we will post the video. Yes, we will. Okay, so then to the negative side, we call it reverse bias. Then the reverse current is very small, but it's almost a constant here. And we call it I0, and it's negative. So if we use the equation to represent this IV characteristic, then it's given by this equation, I equals to I0 times exponential. Q is the charge, VA is the voltage you apply, and then divided by KT. KT is the thermal energy, minus 1. So this equation describes this curve in accurate way. So this is very accurate. And then you can see that when the VA equals to 0, then the I equals to 0. Because here the exponential to 0 means 1. 1 minus 1 is 0. And when the VA is approaching very negative, then this exponential term will approach 0. So you will have current equals to the negative I0, which is here. And then when the VA is positive, then this is almost exponential, because this minus 1 can be ignored, because exponential is a very large number. So then this is almost exponential. And this PN junction is used for rectifier in the circuit if you only want to have one directional current flow. And we're going to discuss about the reasons why the current versus voltage is like this in the later slides. Okay, I got one message from the chat. Maybe you be able to try to turn off the beep. And turn off the beep and name announcement if you prefer not to hear notification or engage. To schedule meeting, go to preference, select audio and video, and from entry and exit tone. So let me try to do this. So you mean Maybe it's in the audio. Or it's actually in the website, maybe. Reference. And audio. Oh, yes, it's beep. Okay, no tone. Okay, I modified it, and hopefully it can take effect. And let me restart sharing. I change it here, this entry and exit tone. All right, thank you. Hopefully now it's better. Okay, so next we're going to discuss why the current versus voltage looks like this. So let's start from the bond model of the PN junction, where we show the dopant here. For the p-type, you know, it's an acceptor, and the acceptor gives you additional hole, but the nucleus of the acceptor is negatively charged. So you have a center with negative charge. And similarly for the n-type, give you additional electron, and the donor's center is positively charged. So then what will happen here at an equilibrium state where the voltage is 0? So you know this is free electron and free hole. They can move around. So if hole sees an electron, they can recombine, or they can be combined. So then that means they're going to be disappear. They're going to be gone. So you can look at this animation. So here we have free electron, free holes. Once they see each other, they will be recombined, or they can be gone, or they disappear. So after they are recombined, what is left here is those non-movable, fixed nucleus of those acceptor and donors. There's no free electron or hole in this region. And we call this region as depletion region. So here we call this region as depletion. And we can divide that into two parts. One is a p-type depletion here, and then you have n-type depletion here. So in total, we have this depletion with WD. And you can divide that into two parts. So this is the bond model. And then we can look at this from the band model as well. So here, this is the energy band diagram you have seen before. So for p-type semiconductor, as you recall from lecture 5, the EFT, the Fermi level, is close to the EV. And then for the n-type semiconductor, the EF is close to the EC. So this is when those two semiconductors are, let's say, far away from each other. They are not interfaced like in the PN junction. If you have individual p-type, like this. If you have individual n-type, it's like this. But now in the PN junction, they interface with each other. So they are one system, actually. So in one system, there is an important conclusion, that is at equilibrium state, where the external voltage is 0, then the Fermi level will align up. That means there's only one single Fermi level in the system. The Fermi level will be flat. But now you see those two Fermi levels are not aligned. So we need to do something to make it line up. So how do we do that? Then once those two pieces of silicon talk to each other, then the Fermi level will line up like this. Now you have a single Fermi level. This is to satisfy the condition the system is in the equilibrium state. Now you have to collect the band edge EC together. So you will see this bent of the band. So the Fermi level will be flat and the EC will be continuous, but then we see the slope here. So this actually happens in this depletion region. So this is the depletion region. This is the depletion region. And then here we see there's a barrier between the p-type and n-type. So this is a barrier, and we call this is built-in barrier. The built-in barrier is given by this formula. We are going to derive that in the next slide. And here the key important message here is that the band of the EC and EV will be bent. And here we have the slope. The slope is telling you that there is an electrical field. If you recall the lecture 5 or the lecture 6, we have the conclusion. If you have a slope in the energy band, that means there's a field. Why there's a field? If you look at the bound model here, you have the fixed charge. From this positive charge to the negative charge, you have electric field. So then in the band diagram, you have the slope, and this slope is negative. That means the electric field to the left. So let me see if there's any questions. Still seems that we have the deep. Maybe that will take effect after we reconnect. But let's move on since we lost many minutes in today's lecture. So let's move on. All right, so then let's look at how to derive this barrier height. And we call this built-in potential. And this is represented in the voltage because here we take the Q to the denominator here. And if you look at the barrier in the energy band, this is Q VBI. So if you use a unit like electron volts, the Q will give you electron, and the V is the voltage, so it will give you electron volts. Okay, so let's look at how to get this VBI. And if you recall the lecture 5, and also your homework, you have done the practice to get the distance from the Fermi level to the band edge. And for the PN junction, we can do the same thing here. So the VBI here, you look at the distance, let's say from the band edge EC to the EFP, we equate B. And then from the band edge EC to the N-type EFN is A. Then the Q VBI actually is a B minus A. So we need to get B and A, and then we can get this Q VBI. So let's look at the N-type region first. N-type is this side. So we know that N-type, the EFN is close to the by this formula. If we use the N-type, let's say the electron density, N equals to the donor density, ND, and then equals to this equation, NC times exponential, and negative QA over KT. A is this distance, let's say EFN minus EC. Oh, sorry, the A I think is defined as EC minus EFN. So then this is the same equation in the last lectures. So you can calculate what is A from this equation. This is similar as your homework. So this is A. And then how about B? B is in the p-type, but we want to get the electron density in the p-type. And you know electron is minority in the p-type. The hole is the majority. But we can always use the NP product. And if you recall the NP product, NP always equals to Ni squared. So then we can get N equals in the P-type semiconductor, we can get N as Ni squared divided by P. And you know, P is given by the doping density Na. And then you can plug in the equation here for the same thing here. This is the distance from the EFP to the EC, which is given by this B, the distance B. So you can back calculate B. And if you back calculate B, then you get this equation. And the VBI is B minus A. So you just use those two equations and do the subtraction. So then you take the KT over Q out, and you have two log terms here. Those two log terms, you know, the subtraction between two log terms. Actually, you can take the log out, and what is left can be division. So you will have this term divided by this term. You take the log out, you can have this term divided by that term, then eventually you can get this equation. Some math here. But as you can see here, the VBI depends on the doping. Depends on doping both N-type and D-type. You have Na and Nd here. And then with higher doping, then the VBI will be higher. So the barrier height will be higher. Any questions? All right. So then let's look at the current components in the PN junction. So here we have 4 components. We have electrons and holes, and electrons will have the diffusion and the drift. Hole will have diffusion and drift. But at equilibrium state, those 4 components should cancel each other. So the net current should be 0. So let's look at why is that. So here is in equilibrium state. That means no external voltage bias. And the electron in the N-type, of course, we have more electrons in the N-type. So here, this is N-type to the right-hand side. And then the electrons are in the conduction band. But the electrons will follow the Boltzmann approximation of the Fermi function, where you have the exponential decay towards higher energy level. So if you recall the Fermi function, it says that the probability to find the electron is exponentially less when the energy move up. So here let's say, draw this schematic to show the distribution of the electron. So basically more electrons to the lower level and exponentially less electrons to the higher level. So the electrons here will diffuse from the N-type to the P-type. Why is that? So in the P-type, the electron is minority. This is majority to the N-type. This is minority to the P-type. And you know the diffusion means when the concentration of the carrier is different, then the carrier tends to diffuse from the higher concentration to the lower concentration. So that's why the electron will move from the right to the left. But the electrons will see this barrier here, this barrier. The electrons with less energy will be bounced back by the barrier. Only the electrons with high enough energy, higher than the barrier height, this QVBI, this one, will move over. So this is for diffusion. And then for the drift, here you look at this electron, and this is towards the edge of this depletion region. In the depletion region, you see there's a slope of the band edge. And if you recall, we said that the electron is like water, always tend to fall down along this slope to lower potential. So this electron tend to drift to the right. So this drift and diffusion will cancel each other at equilibrium state. Similarly, for the hole, here you can see hole like bubble tend to occupy higher level first, and then this hole tend to diffuse, but will be bounced back. Only the hole at low enough energy here will move over this barrier, and then the hole drift will cancel this diffusion. So the hole and electron is just opposite to each other. So if you understand this electron's behavior, then you will understand the hole's behavior here. So the conclusion here is that at equilibrium state, no bias, the drift and diffusion current will cancel each other. The net current is 0. Any questions so far? All right. Then let's look at what will happen if you apply a positive voltage. If you apply positive voltage, let's look at the bump model. Here you have the depletion region. And then positive voltage means what? So here the N side is grounded, and the electrons will inject from the grounded terminal. Electrons will go to the higher potential. Here you have positive voltage, so electrons will inject from the ground terminal. So the electron will move. So that means you have more electrons here. So those electrons will move. So that means the depletion region will get reduced. Because here you have more electrons, then the depletion region will get reduced. The WD, the width, will reduce. Similarly, you can think about the hole is injecting from the positive terminal. And then you have more holes here. Then the depletion region width will decrease. So this is from the bond model point of view. And then let's look at the band model. Sorry, before that, if you keep further increase the voltage, positive voltage, you will get more and more electrons. Because you keep injecting electrons from the ground terminal. So those electrons eventually need to go to the positive terminal. So the electrons here will diffuse over the depletion region and then become the minority in the p-type. The first electron come from the ground terminal to the n-type, and in n-type electrons are majority. But once the electron diffuse over this region, then the electron will become minority in the p-type. And it will tend to move over. So let's look at what will happen from the band diagram point of view. So that's why I prefer to use a band diagram to explain the physical process. So here, this is the band diagram. And this is at equilibrium state. Voltage is 0. So you have the flat Fermi level. And now you apply positive forward bias. So this is positive to the p side. And if you recall the conclusion from the last lecture, we said that positive voltage push down the band. Why is that? This is electrons energy diagram. You have positive voltage, the electrons energy actually will be reduced because the electron is negatively charged. So it will push down the band. previously you have the EFP along with the EFN, but now the Fermi level here is reduced by this QV. You applied this V. And the EC and EV will both push down by the same amount, QV. So everything here will be pushed down by the QV. Or in other words, this barrier height previously is QVDI. Now it will be reduced by this V as well. So this barrier height will be reduced. And now this EFP and EFN will be split. This is no longer equilibrium state because you have current flow. Then the Fermi level can be split into the P side and N side. We could call the Fermi level for the P and call the Fermi level for the N. So this is what happened with the positive forward bias. Okay, so let's look at this schematic again. And this is the electron distribution in the N side. You have this kind of electrons more to the lower level. But now, since this barrier height is reduced, now you have more electrons that can move over. This is diffusion by diffusion. So you have more electrons can diffuse over the barrier. So you have electron flow to the left. That means the current flow to the right. So this is from the P to the N if you talk about the current. But if you talk about the electron flow, then you have more electron diffuse from the N to the P. But the drift current will not change, okay? Because drift current, you need a certain number of electrons to be drifted. And this amount is determined by the doping density of the p-type. So this one electron will remain here. You only have one electron. This one electron will move to the right. But now you have more electrons move to the left. And then you have the large current in the forward bias. And the number of electrons that can move over the barrier essentially depends on the barrier height because of the Boltzmann approximation in the Fermi function. This is the exponential function here. As you change the barrier height a little bit, then you have exponentially more electrons can diffuse over. So that's why the current in the forward bias essentially depends on the voltage. So similarly, you can look at the hole, and the barrier height is reduced. So you have more holes that can move over, diffuse to the right. So overall, if you consider the electron and hole flow, then you have this forward current exponentially depends on the voltage. Any questions here? Hopefully you can still hear me. So I would appreciate any feedback if you can still hear me. Okay, thank you, Zach. So here, this is the forward case. Okay, this is forward case. And then let's look at the reverse bias. Before that, I got one question. Wouldn't the decay of the carrier be into minority bands? Both here, I think we are talking about the decay of this. Yes, both the let's say the p-type and n-type will follow the same kind of exponential decay. Yeah, in this n-type semiconductor, the electron is a majority, right? So still, here you need to follow this exponential decay in the majority carrier here. So this exponential decay does not depend on the minority or majority. if you recall, this is from the Fermi function. This is from the Fermi function. If you recall the Fermi function, you can have the EC, EV, right? And then you have the Fermi level, where the probability is exactly half. And then the Fermi function will be something like this. Right? So this exponential decay is true for the N-type or P-type, doesn't matter. The only difference is that for the N-type, you have more electrons here because the EF is close to the EC. If you think about the P-type, EF is lower, right? So you have less, much less electrons here. But no matter what, the number of electrons here exponentially depends on the any shift of the EF. If you shift EF back a little bit, then you have exponential increase or decrease. If the EF move, let's say move down, you have exponentially a decrease of the electron density in the conduction band. So no matter N-type or P-type. So here, this also applies to here if you think about the distribution. Okay. So what will happen if you apply negative voltage? From the bound model point of view, if you look at this. So for the negative voltage, you apply negative voltage here. So negative voltage tend to pull out the holes, right? If you have a negative voltage here, the hole tend to move to the lower potential, and then electron here tend to move to the higher potential. So this is ground. But relatively speaking, this ground is higher potential than the negative voltage. So electrons tend to go to higher potential, electrons tend to move out. So that means here you are going to move out the holes from here and the electrons from here. As a result, so the depletion width will further increase. This is opposite to the forward bias, where the depletion width decrease. Now the depletion width increase in the reverse bias. Okay, so let's look at the energy band diagram in the negative voltage reverse bias. So we start from the equilibrium state like this. Now the voltage become negative to the P side. So negative voltage will push up the band. It's just opposite. Positive voltage push down the band. Negative voltage push up. So if you push up, then something like this will be pushed up by this QV. Or let's say if you take the absolute value of the V. So this is the P side. You have the increase of the Fermi level and also the EC and EV. As a result, this barrier height will increase. So, any questions? So it's just opposite to the forward bias. You increase the barrier height as a negative voltage to the P side. Then what will happen to the current? So you can look at this schematic again. And you still have this kind of distribution of electrons in the N-type. And you have the exponential decay as you go up the energy level. But now even the electron to the highest level, still they tend to diffuse out because you have N-type here, P-type here, you have more electrons to the N-type, less electron to the P-type. Naturally, by diffusion, then this electron tend to move to the left. But then this barrier height now is increased. So all the electrons here will be bounced back. And then for the drift current here, still this electron, you have minority electron here, so you only have one example. So this electron still will fall down the slope. So this is a drift. And drift current will dominate in this case. But the drift current is very small in the reverse bias. Why is that? Because this current depends on how many electrons are available at the edge of the depletion here. So you have minority carrier here. The electron density is low, so the number of electrons that can fall down is limited. So the current is small. So here still this electron tend to fall down. You have the drift current, but the current is small. So that's why if you recall the IV towards the negative side, then the current tend to approach a constant current. That means all the electrons here available will be swept to the other side by the drift. But you don't have more electrons here, so the current will not further increase. So the current will approach this negative I0. So similarly, you can argue for the hole. All right, so this is a summary of the PN junction at 3 states. First one is equilibrium state, where the voltage, external voltage is 0. Forward bias, you apply positive voltage to the p-type, and the reverse bias, you apply negative voltage to the p-type, and this is a corresponding band diagram. So equilibrium state, single EF flat, and then forward and reverse bias, the EF will split. But then you need to look at the positive voltage here push down the band, the negative voltage here push up the band. So the barrier height is reduced or increased by the external voltage. And in the forward bias, then the diffusion current dominates. So the diffusion is from the N for the electron is from the N to the P. And then for the reverse bias, then the drift current will dominate. And the drift current, let's say in terms of electron flow, is from the P to the N. Any questions? All right. So then, since the reverse bias PN junction is, let's say, has a very small current, so we can almost ignore that current. Then it's more like a capacitor. And here, if you think about the bond model, where we have the depletion region, where that means you don't have any free carrier, or it's like an insulator. So you only have the carriers from the edge of the depletion region. So it's like you have a plate capacitor in this case, where the capacitance is given by the epsilon of silicon, if the semiconductor is silicon, divided by the depletion width is the distance between the two electrodes in the plate capacitor. And this is the junction capacitance normalized to the area. So this is capacitance normalized to the area. So what area? If you think about a piece of silicon, you have the cross-sectional area. And then if you normalize the capacitance per unit area, then you get the epsilon silicon divided by the depletion width. And as we discussed earlier, as you increase the forward bias, let's say you have more negative voltage applied, then you're going to have larger or wider depletion region. Then the junction capacitance will decrease. You have larger W, then the junction capacitance decrease. Okay, so this is the PN junction in the reverse bias. It's more like a capacitor, and actually it's a variable capacitor, depends on the voltage, because this capacitance will change with the voltage, because the depletion width will change. All right, so why do we talk about the PN junction? Because PN junction is essential in the MOSFET structure. And we are going to discuss MOSFET in great details in the future lectures. But today, let's have a very quick preview of the MOS cap and the MOSFET. What is MOS? It's metal oxide semiconductor. And if you look at the cross-sectional view of the device structure, you have a metal, like a gate, and then we have this oxide, and in this case, silicon dioxide, and then we have the silicon substrate, or sometimes we call it the silicon body. So this is your wafer. This is your starting in substrate, and then you build on the structure on top of the substrate. So if you only have the 3 layers like this, then this is a MOS cap. It's 2-terminal device. It's an MOS capacitor. And if we want to make the MOSFET, that is a MOS field effect transistor. This is one type of transistor, and this is the building block for all the digital computers today. So this MOSFET, the difference is that compared to the MOS cap, then here in the silicon substrate, we need to do some doping. Okay, so we can start with a P-type body, and then we have to dope the left end and right end with N-type doping. And with this kind of configuration, this is N-type MOSFET. In short, we call it NMOS with the N-type doping. And after you dope those 2 regions, then those 2 regions has a name. So this is called source. This is called the drain. And then you have a gate here. And then the body may have a contact. So essentially, you have 4 terminals. And typically, we don't use a body contact. In the real circuit, in many cases, we are going to deal with 3 terminals, gate, source, and drain. Okay, so the MOSFET, at the very high level, you can think it's a switch, nebulite switch. So basically, the gate is a control terminal to determine whether you have current flow between the source and the drain. So here, if the gate voltage is large, then you will turning on the MOSFET, then the current will flow. If this is an NMOS, let's say this is NMOS. And the current flow is from the drain to the source. But actually, the electron flow is opposite to the current. So the source provides electron, and the electron are gathered to the drain, or the electron flow sink to the drain. So that's why this is called source and drain. Or you can think this is a faucet, if you wish. Basically, 3-terminal device. You have a valve to control. This is a control terminal. And let's look at the structure of the MOSFET. Again, this is the gate on the top, and then between the gate and the silicon, we have the oxide. This is the insulator. And then in silicon, we should have the doping. And in this NMOS case, we have the P-type substrate or P-type body and N-type source and N-type drain. So this is for NMOS. Later, we'll talk about the PMOS. So in this case, you see that actually in the substrate, you have the 2 p-n junctions here. So this source to body, you have p-n junction because this body is P and the drain is N. So you have 2 p-n junctions here. And here there's an important conclusion. That is, in the normal operations of the MOSFET, we need to keep the 2 p-n junctions here to be at equilibrium or reverse bias. No forward bias. Because we don't want large leakage current from the substrate. If you forward bias, for example, somehow for the body contact, you apply positive voltage, high voltage to the body, and then you ground source and drain. Then this PN will be forward bias, right? So the PN from the, let's say, body to the source or the body to the drain will be forward bias. That means you have large current flow from the body contact to the source or body contact to the drain. This is not good. This is not what we want. And because that means your gate will lose the control of the channel. We will talk about this later in the next lecture. So the MOSFET, we want the current only conduct at this surface between the silicon and the oxide. And we call this channel. We only want this current flow to be controlled by the gate. We don't want current flow down to the substrate due to this forward bias PN junction. This will cause short circuit in your chip. So we want to avoid that. So in the normal design, we should be careful. The body, for example, in the MOS, typically is grounded. So we don't apply high potential to the body. And then if you look at the band diagram of the MOS, as we showed in the previous slide, if you look at the MOS structure, you have source and drain N-type, and the substrate P-type. Then you have your gate here, source and drain. If you cut along the channel direction like this, actually you have two PN junctions back to back. If you draw the energy band diagram along this channel, you will see something like this. And at equilibrium state, when the voltage VDS between the drain and source, there's no voltage. That means equilibrium state, you will have a single Fermi level here, EF. And then we have the two PN junction back to back. So you have NP as source to body, and then body to drain, you have PN. So if you draw the band diagram along the channel for the MOSFET, for the N-type MOSFET, you will see this kind of band diagram. You have two PN junction back to back. All right. Any questions? So today's lecture, we basically talk about the PN junction, and I think what is important here is understand the current versus voltage. Like here, why this is a exponential IV to the forward bias, and then almost a constant to the negative reverse bias. And the best way to understand that is this kind of band diagram, where you have the equilibrium state or the current component cancel each other. And then when you apply the voltage, then you split the Fermi level, push down the band for the forward bias. Now you have more diffusion current. And then if you reverse the voltage, you're going to push up, and then the drift current will dominate. The drift current is small. So I think that's the key messages we want to deliver in today's lecture. All right, I apologize for the technical challenges we faced in the BlueJeans. Hopefully next time the BlueJeans can be up. But we're going to keep this WebEx as a backup plan in case the BlueJeans doesn't work. And also I will try to edit the videos I recorded. So hopefully we can have a better quality video for the YouTube channel if you wish to watch after class. And then the homework 2, as I said earlier, is posted, and you should be able to solve most of the questions except the last one. We are going to discuss that in the lectures on Thursday. All right, that's it for today, and thank you for your patience. All right, bye-bye.